It looks like we can turn to our first talk. So that'll be with Richard. Richard Hollenbach is a doctoral student at Duke University who was awarded a space grant for the 2021-2022 school year. And he's conducted research in investigating unsteady aerodynamics in turbofan aircraft and turbopump rocket engines exhibiting non-synchronous vibrations. This is actually his second NC Space Grant Award, and it expands on his previous research. So Richard, whenever you're ready, the floor is yours.
All right, thank you so much. I'm sharing my screen and we're good to go. All right, so good afternoon, everybody. As mentioned, I am Richard Hollenbach. I am actually recently defended my PhD at Duke University. So I'll be presenting my talk today on unsteady pressure analysis of the three-stage turbine. Specifically, I'm looking for non-synchronous vibrations, also known as NSV. Okay, so turbomachinery has been around for a long time, but it's some of the most powerful machines there are today, from your jet engines to your rocket pumps. And there are multiple engine companies that design this turbomachinery, from Rolls-Royce to General Electric or Pratt & Whitney. And they employ either their own homegrown codes or commercial software such as ANSYS CFX. But at the center of it all is consortiums such as the GUIDE Consortium, which solves the problems that are out there faced by engine manufacturers or in the software by studying these phenomena. This particular set of vibrations, called non-synchronous vibration, was actually found and published in a paper in 2003. You can see the left-hand side is some strain gauge data that was on a compressor blade, and it reacted at the first torsional mode with pretty high response at 2 frequencies. This work was brought to Duke University to try to recreate it, and we can see on the right-hand plot that the final frequency was about 9% off. So more studies were required. So specifically on my work, I took a very simple configuration to start, and that was a circular cylinder. So you can see in the 2 videos here, well, we can study an unlocked case where an unsteady aerodynamic instability, such as vortex shedding, if it's distinctly far away from an enforced or natural frequency, you get 2 separate frequencies and low amplitudes of vibration, so it's pretty safe. And that's that bottom case here. However, when that vortex shedding locks in or jumps onto the natural mode of vibration, you get large amplitudes of lift, large vibration, and that can cause blade failure in your jet engine. The reason I started with the simple cylinder was I wanted to, get some results pretty quick and understand the flow physics that was going on within this case. One day we hope to build a design tool for engine manufacturers, because there's nothing out there right now. Now, moving on to a slightly more representative case, I studied the NACA 0012 airfoil, and we can see the same phenomenon here. So in the top, you can see that the vortex shedding locks into the motion of the airfoil. Now, instead of translating up and down like the cylinder did, the airfoil now pitches around its quarter cord. And at the bottom case, you can see an unlocked case where the frequencies have separated to unsteady pressures due to vortex shedding and then due to motion. But at the end of the day, we really want something that represents turbomachinery. So in a partnership with Hanover, Germany at Leibniz University, a 3-stage turbine was constructed. And you can see some pictures here of a former 5-stage turbine rig converted to a 3-stage turbine rig to study this phenomenon in a true representative format. Now, they did all the experiments, and to support it, as a graduate student, part of my dissertation was to do all of the CFD, or computer simulation analysis. So rather than simulating the full engine, which is really large and really complex, we simplified it to a single passage. So you can see all 6 blades in this passage. And then we use periodic boundary conditions to simulate it being a full 360-degree circle. What are some of the results that we are looking for? So as I mentioned at the beginning of my talk, I'm searching for this non-synchronous vibrations. So when I ran the CFD, I would get a pressure plot on either some of the rotors or maybe at some of the locations where experiments are collecting data. And you get the bottom left time signal. And then through fast Fourier transform analysis that I did in MATLAB, I could identify potential frequencies. So on the left in the green circle, you would see what we think is the non-synchronous frequencies. And then on the orange is blade passing or other frequencies that we know we would expect to find in this experiments or in the computational simulations. CFD is really great though, because we can actually visualize what's going on in the flow here. So I performed a lot of flow visualization. The first plot is a mid-plane plot of the streamline. So you can see the behavior of the flow around all of each stage and each blade. We can see a vortex actually at the last one. And then we can plot things like entropy, calculated variables through CFD, and you can also see the vortex there. I'm coming up at the end of my time, so I do want to thank the North Carolina Space Grant for their support these past 2 years. I'll take some questions if there's time, otherwise we'll get to some questions later. Thank you.
Great, thank you, Richard. I'm not seeing any questions in there at this point, but first of all, congrats on the PhD, and I was wondering if you had any future plans after graduation.
Absolutely. So I accepted a job with Exponent Consulting. They do scientific and engineering consulting down in Atlanta. I'm going to be doing thermal sciences, which encompasses aerospace, heat transfer, fluid dynamics.
Great. Okay, there is one question here. So based on what you've learned, what are future directions for your research, and where do you see future applications of the information you gleaned from this project?
Absolutely. So the goal is one day to have a design tool that Rolls-Royce, Pratt & Whitney, General Electric could use to design their engine to avoid this phenomenon from actually occurring. That design tool hasn't been built yet, but the next steps would be taking what we learned from this process and designing that tool.
Great. Well, thank you, Richard. I think we're going to move on at this point, but great talk.